In this section, now we're going to start discussing distribution functions. First, we're going to start with the radial distribution functions. And to see where those come from, we're going to start by looking at the norm, or the integral that corresponds to the norm of the hydrogen stationary states that we've derived previously. So remember, the states that we derived previously have this radial part times the spherical harmonics. And if we wanted to just verify that this thing was normalized, the integral that we'd end up doing would be the integral over all space, but this is in spherical coordinates, and so it would be an integral from 0 to infinity times dr, integral from 0 to pi d theta, integral from 0 to 2 pi d phi. Then we multiply by the magnitude squared of the eigenstate itself, so n, l, m, r, theta, phi, and this is magnitude squared. But because we're in spherical coordinates, we're not done. We still need to multiply this by the actual volume element. And so this gives us the r squared sine theta. Okay, so now if we break this up in terms of the radial and the angular parts, we should get a product of two different integrals. So on the one hand, we have the r integral, which has r squared dr, and then we have the angular integral, which we're just going to write in terms of the solid angle like this. And this is magnitude squared as well. And what we know is that the spherical harmonics are defined so that this is normalized. And so this is just equal to this. And if this is supposed to be a normalized eigenstate or a normalized wave function, then this thing ought to be equal to 1. And the norm by itself isn't what we're interested in. What we're interested in is the probability distribution. Or from looking at the norm, we can see what the form for the probability distribution ought to be, right? And so let's be a little bit more concrete. What we want is we want a function p of r, so that p of r dr gives us the probability of finding the electron at radius r from the proton. Now, by just thinking about this for a second, this is a probability of finding an electron in a particular place. If we integrate this probability over every possible distance, and every possible distance goes from 0 to infinity, then this integral should give us 1, right? So the integral of p of r dr over all space should give us 1 because the probability of finding the electron somewhere ought to be 1. And so what this tells us is that our candidate for p of r should not be r squared, it should actually be big R, so it should be the radial function squared times r squared, so times the radial part of the volume element. And so this is the actual radial distribution function that we should look at. And this will affect our interpretations in subtle ways. So the way you can think about this is that this r squared is kind of like a weighting function. And it's taking into account the fact that for larger r, there's actually just a heck of a lot more points that count as being that distance away. So for, if r is equal to 1, there's a sphere of radius 1 that is all 1 unit away from the proton. But at a radius of 2, the surface area of that sphere has just grown by a factor of 4. So there's 4 times as many points that all have the same distance away from the proton. And this r squared takes that into account. So now let's see the consequence of this with some actual radial distributions. All right, so what we're seeing here is a comparison of the value of the radial function at different radii, and then the value of the probability distribution function. And remember, these have very different interpretations that you have to be careful of. We have in the first row is a radial distribution function that corresponds to the 1s stationary state, or the 1s orbital. and then we have the radial distribution that corresponds to the 2s, and then on the bottom row we have the radial distribution that corresponds to the 2p eigenfunctions. So let's start by looking at the 1s radial distributions. So notice if we look at the value of the radial function itself, right? So this is just the value that hasn't been weighted by the volume element at all. Then the most likely position is right at the nucleus, right? So it goes up to this, so almost 2 right at the nucleus. And this is by far the maximum of what's going on here. So if you want to know what the highest value of the eigenfunction was, then you'd look at it in this way, and you'd see that it attains its maximum at the nucleus, or at the position of the proton when r is equal to 0. But that does not mean it's the most likely distance away from the proton. So when you weight this by the volume element, when you weight it by this r squared, so that now what you look at is the proper probability distribution function. Then what you see is that it achieves its maximum likelihood, or its maximum probability of being at a particular radial distance some bit away. So somewhere around, in this case, it will be 1 Bohr radius. Okay, so this might sound like contradictory information, but it's really important to have this straight. So the maximum value of this eigenfunction, which would be the wave function for a 1s orbital, is not the same thing as its most likely position away from the nucleus, most likely distance. And that's simply because this gets weighted by the volume element, which goes very quickly to 0 as r goes to 0. And now you see the same thing for 2s, right? So 2s state has a maximum again at r equal to 0, but when you weight this by the volume element, the probability of finding it at 0 is essentially 0, and then it has a maximum pretty close to that. So pretty close to the core, it goes to a maximum. And again, you see the same exact thing for the 2p, although now in this case, the maximum is not right at r is equal to 0, it's a little bit away. But still, once you weight this thing by r squared, it shifts out where the maximum is. And so it's no longer just the case that the value squared gives you the right thing, because you have to weight it by the volume element. The other thing you can see from this is that psi 2s has a radial node, right? So the value of the wave function changes sign, or the value of this eigenfunction changes sign. That means that in this spot, there will be 1 radial node for the psi 2s. But then you notice for psi 2p, there is no radial node whatsoever. And so if we summarize this, we have 0 radial nodes for the 1s, 1 radial node for the 2s, and then 0 radial nodes for the 2p. Now let's finish this analysis by taking a look at the n equals 3 states. So what we have up here now, this will be the radial portion that corresponds to psi of 3s, psi of 3p, and psi of 3d. And we once again see basically the same type of structure, right? So psi of 3s has a maximum value. The actual eigenfunction itself takes a maximum value at r equals 0. But when you weight this by the volume element, you find that the probability of finding it right at the nucleus is basically 0. And instead you get this maximum that's close to it, but not exactly at 0. And again, in each of these cases, as you weight by r squared, you push out where the maximum value is further away from the nucleus. Now if we go through and count the nodes again, so the 3s, we see 2 different points where the value of the eigenfunction changes sign, which leads to a 0 in the probability distribution right there. For 3p, we see 1 point where this happens. And for 3d, we see none. So we summarize this as 2 radial nodes, 1 radial node, and 0 radial nodes. So from analyzing this pattern, what we can conclude then, I'll write this over on the right-hand side, RNL has n minus L minus 1 radial nodes. All right, and we can make sure this fits for the data that we've observed so far. So we saw that for n equal to 1 and L equals 0, where there were no nodes, and so if we do 1 minus 0 minus 1, we have 0 radial nodes, so this fits all of the n equals 1 states. Previously we saw that for the n equals 2 states, the 2s radial function had 1 node, and so this is 2 minus 0 minus 1 gives us 1 radial node, but then the 2p had no radial nodes. And then looking here again, we see that the 3s, so this would be n equals 3 minus 0 minus 1 is 2, has 2 radial nodes. 3p has 1 radial node, and then 3d has no radial nodes. And now the last thing we want to point out in this section is that if you look at what's happening close to the nucleus for a given n value, so this is all the n equals 3 radial functions that you see that for lower values of L, so for lower angular momentum, but for still the same n value, you get much more penetration into the core close to the proton. So let's color this a little bit. So what I'm talking about is this little bit of space here relative to its corresponding position here or over here in the 3D. And this is more or less what we predicted by thinking about what happened with this effective potential that we solved originally in order to get the radial equation in the first place. Remember, there was this L times L plus 1 over R squared term that was added to the 1 over R Coulomb potential, and this defined what we called the effective potential. And what you saw from this was that because when R gets close to 0, 1 over R squared will dominate this. This ended up putting more or less a barrier, saying that higher angular momentum states could not penetrate into the core as well as lower angular momentum states. And we're seeing the evidence of this. This, however, does not mean uniformly that higher angular momentum states are further away from the nucleus on average. And in fact, if you look at these distribution functions, you notice that this 3s state extends much further out, right? So it takes kind of a lot longer for this thing to decay to 0 relative to the 3p state or the 3d state. So if you just draw a line down at the r over a naught equal to 20, right? If you compare these three, these are all the same points, then you'll notice pretty clearly that the 3s orbital is much more likely to be found beyond this point than the 3p or the 3d. Okay, and in fact, the average position, the average distance for the 3s is longer than the average distance for the 3d, right? And these might sound kind of contradictory, but they're not, in fact, right? So this is saying that the 3s can penetrate the core more, but it also has a much longer tail. And so it's also found very far away. This puts the average somewhere out this way. Whereas the 3D orbital does not penetrate into the core really at all, but it does have a tighter distribution, and so its average value will be somewhat closer to the proton. Now in the next video, we'll start talking about the total probability distributions, including both the radial and the angular components,